Hello, ladies and gentlemen. Mr. Miller here with your 3.2 linear function notes. At the end of this, you will be able to identify linear functions using graphs, tables, and equations. Second part, you'll also graph linear functions using discrete and continuous data. All right. First term, linear function. Linear function is a function whose graph is a non-vertical line and it must have a constant rate of change. So it must have a constant rate of change and can be represented by a linear equation. Using two variables, or another way to say it, in two variables. So those two variables usually will be x and y, but it does not necessarily have to be x and y. Those are just the common ones. All right. So two graphs here. So linear function means non-vertical line, obviously, but it must be a line. So it can be anything that's a non-vertical line. So it has to be straight. It cannot have any curves. So if we're just looking at the two graphs here, obviously we notice a huge difference. One has a giant curve in it, and one has a nice straight actual line. So just looking at it, making sure that your function, if it is linear, has to be a straight line. So as a curve, this is non-linear, because again, we have a curve, and this one is a linear function. It's a nice straight line, no curves. And also, it is not vertical. Remember, vertical goes up and down. Moving on. So that's just looking at graphs. Second part, using tables to represent either a linear or a non-linear function. So based off our definition up there, yes, we could transfer all this to a graph if you wanted to and plot those points and actually look at it visually if you wanted to. But if we don't want to take the time to do that, here is your second choice. So again, our input here, again, these are our functions because all of our inputs are different. So every one of these is a function because the x value, that independent value, is all different. So again, we have a function. We do know that. So no tricks there. Now we want to make sure that it is linear. So if it's linear, it has to have a constant rate of change. So we're going to look at our y's. What is the constant rate of change for our y's? Also, you can look at the constant rate of change for your x's as well. So here, constant rate of change is a difference of 10 each time. And on the bottom, we have a difference of 4. So we're decreasing by 4 each time. So those are both constant. So we do have a function. So this is a linear function because it's constantly changing. The top is changing by 10s. The bottom is decreasing by 4s each time. So we'd anticipate that pattern to continue. For our second one here, looking at our top numbers, they're increasing by 1 each time. Our bottom one looks like here, if I do my adding and subtracting, that would be 3, then we have 6, then we have 12. So actually it's a multiplication for that pattern. So we're actually multiplying by 2 to get to 6. We multiply by 2 again to get to 12. And we multiply by 2 again to get to 24. Again, constant. So this one's changing by a +1. These are doubling each time. So again, a nice linear function. Guess we'll put function underneath all of these. Last one here. So starting at the top, looking at those numbers, so we have an increase of 1, then we have an increase of 3, then an increase of 5. So that is a constant change. So we'll have to see on the bottom here. So because we are increasing by our odds there. Next, checking the bottom here. Looks like we got increase of 2, increase of 6, increase of 10. There is nothing constant about our change in our y's, unfortunately. So even though we might have had odd numbers here as a constant for the top, it did not match up because we went a difference of 4. Yeah, because we started with 2, so it's a difference of 4 after a difference of 2. So not constant, so nonlinear function. And again, I guess I'll go back to this, like, these aren't constant either because it is increasing by 1 and increasing by 3, so it's jumping, should be increasing all by the same on the top there as well. So again, just to recap, again, if you're having a hard time telling how these are, you can graph them out and see, does that represent a line? But obviously, something like this, you'd want to make sure you have graph paper to graph those out to see if they truly do fall on the same line there. All right, quite a few terms here on the back that we have to get through. So solution of an equation is an ordered pair. And that ordered pair is going to be our xy. And whatever that xy is, that is going to make the equation true. So that makes the equation true. So that would give us our solution. So making it a true equation there with our xy ordered pair. A discrete function is a set of input values that consist of only certain numbers in an interval. So we're picking out like whole numbers as an example. So discrete, so I might kind of reference whole numbers there. Again, input being our x value, our independent value, our domain there. Our continuous function is a set of input values that consist of all numbers in the intervals. So that would be like going out further, so like our decimals / fractions. So we get more of a range with our continuous functions, where discrete is set numbers there. All right, not always whole numbers, but set numbers. All right, so we can have like 1.5, then 2.5, then 3.5. Those are set numbers. Where continuous means we are going to see more decimals and fractions with our whole numbers, and obviously probably should have put range there. Range would be a better word of numbers for that. So put range above. Some examples of discrete quantities. So again, just to clarify here, it would be like our integers. If they said 1 to 5. So if we're looking at a number line, ladies and gentlemen, 0, 1, 2, 3, 4, 5. Let's even have put some negatives on there because we're going to have negatives also. If we're doing an example of discrete quantities, our discrete quantities are going to be the actual whole numbers. So one particular whole number, one particular value for each interval there. So 1, 2, 3, 4, and 5. Those are our discrete quantities there. Versus continuous quantities, that would be all numbers 1 to 5. So on our number line, again, -1, 0, 1, 2, 3, 4, 5. It would look like this, our range, our inequalities. So again, 1 less than or equal to x, which is less than or equal to 5. Inequalities popping back in. So again, the difference of discrete applies to kind of like whole things. Continuous, it's very fluid there. All right, last little part here is we have two graphs. So we're trying to figure out, are these discrete or continuous examples here? So it says the linear function y equals 15.95x represents the cost y in dollars. All right, So that is our dependent variable there, our range of X tickets, our input domain there for the museum. Each customer can buy a maximum of 4 tickets. Find the domain of the function. Is it discrete or continuous? So our domain, which I kind of just hinted at this, is our tickets. And just putting them in brackets here. The choices are 0, because they don't have to buy any. 1, 2, 3, and 4. So a customer can buy a maximum of 4 tickets there. So doing a little calculation here with our formulas. So 15.95 times 0, 15.95 times 1. I'll move this up. 15.95 times 2, 15.95 times 3, and 15.95 times 4. We got a little calculator work because we're going to be graphing these out. So obviously 15.95 is, oops, the 1, not the 0. Jeez. We'll point that up there, put 0 there. Then 15.95 times 2 gives us our 31.90. 15.95 times 3 is 47.85. And then 15.95 times 4 gets us 63.8 or $63.80. So here, these, reading the question, you're buying a ticket. So when you buy a ticket, you're getting a whole object. You cannot purchase part of a ticket. You either have to purchase the whole thing or nothing at all. That tells us whether it's discrete or continuous. So considering I cannot do a part of a ticket, this is going to be a discrete graph here. So I will have points on my graph. I will not have a continuation like continuous would be. So here, just kind of looking at your data. So obviously we're going 0 through 4. So it looks like I can skip every 3 lines here just to spread it out. So there's 1, there's 0, skip 3 lines, skip 3 lines, and skip 3 lines. There's my 0, 1, 2, 3, and 4. Then just based on what you want to do here on your y-axis. Some people do possibly whole numbers. If you want to do whole numbers, that's fine. If we want to do more exact data, considering this is exact data, it goes up 15.95 every single time. You could actually put that on the lines if you want. I'm going to go kind of like rough estimate here. Just to show. So again, I think I can skip like every 3 lines here. So if I'm doing a rough estimate, cost me roughly $16. Then skipping 3 lines, I have $32. And skipping 3 lines, I have my 48. And then skipping 3 lines, I have my 64. So again, obviously, if we don't buy any tickets, that's 0. At 1, we're going to just be below that line. So there's my dot. At 2, we're going to be just below the 32. And then again, if you want to put 15.95 on that line, obviously you'd put the dot right on the intersection there. And 3, but again, my data is over here so I can reference it also. That's just going to be below 48. And for number 4, follow my line up. That's going to be just below 64. So again, here's an example of discrete. We just have our points. We do not connect those points because we cannot get anything between buying a ticket and not buying a ticket. You can't buy half of a ticket. It's not possible. So that's what your graph would look like. Next one, and actually last one here. So our protein bars contain 130 calories. The number C for our calories is a function of the number, or number B, of bars that the person is eating. Experimental evidence shows that you can eat a maximum of 5 in one setting before becoming ill. I don't know if I would want to eat any of these. But anyway, so does this situation represent a linear function here? So obviously our calorie consumption, ladies and gentlemen, is based off how many calories there are in each bar, and there are 130 calories in each bar. So depending on how many bars, so again, that X, like our X, that's our input there. That's our domain, how many bars we eat. Is going to determine how many calories we have there. So does this situation represent a linear function? And yes, it does. Explain why. Because we have a constant change. For every bar, it's 130 calories. One bar, 130. Second bar, 130. Third bar, 130. Now, if our bars were changing all over the place, then, we're not going to have necessarily a linear function there. It might be more curved. So, but this one stays at 130. So yes, the constant rate of change is 30. 130, excuse me. Find the domain of the function. Domain is how many bars we're eating. So our domain is, again, using brackets. If we eat 0 bars, we eat 1 bar, 2 bars, 3 bars, 4 bars, all the way up to 5 bars. So we want to graph our function here. So before I graph my function, I'm going to do a little table. So I have points to actually graph out here. So 0, 1, 2, 3, 4, 5. Obviously 0 plugging into my formula gives me 0 back. If I eat 1 bar, that's exactly 130. 2 bars is 260. 3 bars, 390. And again, this might where you switch over to a calculator, but 4 bars is going to be 520, and 5 bars is 650. We're just increasing by 130 each time. So again, because that was our constant rate of change there. From here, we kind of have to think about it. Is this going to be discrete or continuous? So we're eating bars. Can you eat a part of a bar? And the answer is yes, you can eat a part of a bar. I don't have to eat the whole bar. I could just eat half of it and save the other half for later. Or I could eat a fourth of that bar and save the half for later. All right? If I eat a half of it, I'm going to get half of the calories. So I'd only get 65 calories. If I ate a fourth of it, obviously I'm getting a fourth of the calories. So the calories get divvied up amongst how much of that bar you actually eat there. So this is going to be a continuous graph. And this is what a continuous graph would look like. Again, start with 0. Whoops. And then we can go, I'm going to go every 2 lines here. 1, 2, 3, 4, and 5. And I'm going to do every 2 lines. And I'm going to go my constant rate, 130, 260, and just keep on going, 390, 520, and finally 650. Obviously, if we eat 0, that's 0. Plotting our points, if we eat 1, that's 130. If we eat 2, that's 260. 3, 390. So these are all falling on the intersections. 4, 520, and 5, 650. Considering it is a continuous, we get all the points in between. So there's your difference between continuous data. So we can definitely have all of this. So as you can see, if I have half a bar, I definitely can eat that. I can eat 1.5. I can eat 3.5 if I want. Again, I don't want to eat anything past 5 because I guess it makes you sick. So thank you, ladies and gentlemen. If you have questions, please ask any of your teachers. Also, please sign up for any of those office hours if you need office hours times, or send an email if you have questions.